Hello everyone. We have learned a number of methods for simple circuit analysis, that is the equivalent transform method, etc. Today we will study some systematic analysis methods for solving complex circuits by equation formulating. Firstly, let's review what we have learned. For a circuit consists of n nodes and b branches, we can write the elements constraints for each branch. There are b equations, while for the n nodes, we can get n-1 independent KCL equations and b-n+1 independent KVL equations. Then the total number of the equations is 2b. There are 2b variables in these equations, voltage and current of each branch. Solving these two equations, we can get the voltage and the current of each branch. We call this method as 2b method. In theory, we can solve all circuits with the 2b method, but in fact we hardly use it to solve real circuits or problems, because the number of the equations used in this method is too many and very cumbersome for solving. So we introduce many kinds of the equivalent transform methods which can simplify a complex circuit. For example, we have introduced the serial panel connection, the balance bridge, the delta transform, and for the circuits containing dependent sources, we can find its equivalent resistance by using U to I method or I to U method. They are all equivalent transforms of resistors. While for the power source, we also introduce the equivalent transform between the real voltage source and the real current source. But each kind of these equivalent transformations is applied to a kind of specific circuit structure. If circuits don't have these specific topologies, of course, these equivalent transform methods have no way to apply. That is to say, when solving a complex circuit, especially solving it by a computer, these equivalent transform methods seem a bit powerless. So we now begin to learn some systematic approaches for solving the complex circuits. For any circuit, we can use this method to list a set of equations directly according to a certain rules. Solving these equations, and we can get all the voltage and the current of each branch in the circuit. We firstly introduce the branch current analysis. The so-called branch current analysis is a method that writes equations in terms of the branch currents. Take this simple circuit as an example. It has three branches, two nodes, that is A and B, and three loops. We can draw them like this. There is a large loop here. Now we write equations in terms of the branch currents. There are three branch currents, that is I1, I2, and I3. Firstly, we write the KCL equations for the two nodes. We have I1 plus I2 minus I3 equals 0 for node A, and minus I1 minus I2 plus I3 equals 0 for node B. Obviously, there is only one independent equation. Then we write the KVL equations for the three loops. For loop 1, we can obtain that R1 times I1 minus R2 times I2 equals the voltage rise of all the voltage sources, that is minus US2 plus US1. Look at loop 2. In loop 2, the left part is the voltage drop of all resistors, that is R2 times I2 plus R3 times I3. The right part is the voltage rise of all sources, that is positive US2. Look at this large loop, loop 3. We can write its KVL equation. It should be R1 times I1 plus R3 times I3 equals US1. Observe these three equations. We'll also find that there are only two independent equations. In fact, you can get equation 3 by adding equation 1 to equation 2. We can expand this conclusion to the general circuits. For a circuit consisting of B branches and N nodes, we can write out n-1 independent KCL equations and B minus n plus 1 independent KVL equations. The number of the KCL equations corresponds to the number of the independent nodes, and the number of the KVL equations corresponds to the number of the independent loops. The total number of the equation is B. Because we write the equations in terms of branch currents, now there are B equations for solving B variables. Of course, we can find the current of each branch. According to the element constraints, we can further get the voltage of each branch. Thus, the whole circuit is solved. Here, we'll discuss more about the selection of the independent nodes and the independent loops in the circuits. It's simple for the independent nodes. For n nodes in the circuit, we choose any of them as a reference node. The remaining n-1 nodes are independent. While for the selection of the independent loops, it's simple for the planar circuit. We can choose its meshes as a set of the independent loops. For the circuit just now, it's a planar circuit. We can choose such two meshes as a set of the independent loops. If it is a non-planar circuit, just remember, each new loop should contain at least a new branch. Then we can select a set of the independent loops. Of course, this rule also applies to the planar circuits. Okay, let's summarize the steps of the branch current analysis. The first step is to determine the reference directions for all the branch currents. Take this circuit as an example. We firstly determine the directions of the branch currents as I1, I2, and I3. Of course, the directions of each branch can be determined arbitrarily. Secondly, we should select n-1 independent nodes and write out the KCL equations. For instance, if we choose node B as a reference node, then we only need to write the KCL equation for node A. Thirdly, we select B minus n plus 1 independent loops and write the KVL equations. For a planar circuit, we only need to select its meshes as a set of the independent loops and write the KVL equations. The fourth step is jointly solving these equations and get the currents of the B branches. Finally, according to the branch currents and the element constraints, we can get the voltages of the B branches. Thus, the whole circuit is solved.